Welcome back to the Mobile Edge Forum. For this next session, it's a pleasure to introduce Stephen Douglas, Head of Market Strategy, and Rich McNally, Senior Director of Mobile Service Strategy, both with Spirent. They're going to give us a deep dive on real-world edge network testing experience and talk to us about the importance of end-to-end testing in delivering service-level agreements. So, gentlemen, thank you for joining us, and I'm going to turn the floor over to you.
Perfect. Thank you, Sean, and very good to be here today. So in today's presentation, we're going to have a closer look at end-to-end testing of the mobile edge to deliver on SLAs. And my colleague here, Rich McNally, in the second half of this presentation will share insights on new testing methodologies, best practices, and results from actual live benchmark testing that we're involved in today. But first, let me set the scene on the opportunity for mobile edge-enabled low latency applications and why end-to-end testing is going to be pivotal for this. So I think we're all pretty aware that 5G has broader ambitions to be more than just a consumer servicing technology. And it has these ambitions to become an enabler for all types of economic sectors, including our manufacturing plants and processes, our transportation systems, healthcare, the energy sector, and mobile gaming, to name a few. And one common denominator across all of these sectors is that they require strict demands on both low latency and reliability. And it's fair to say that in today's mobile networks, latency is not always as low or as consistent as we would like it to be. In fact, most cellular networks today which service have latencies which can fluctuate between 20 and 75 milliseconds plus. So if 5G is going to serve these economic sectors, then it needs a plan on how to deliver reliable low latency. And a plan is what the standards bodies have set in motion. And you see, ultra reliable low latency communications is one of the three defining features of 5G. And the 3GPP standards bodies has set an ambition to get latency on the air interface to less than 1 millisecond and provide enhanced reliability. The standards bodies are also defining additional capabilities to help reduce the overall end-to-end latency beyond that air interface and right through the new core network and out to the internet. And you can see here on the right-hand side of the chart a number of key features and enhancements that are coming through the 5G releases over the next coming years. So this raises the question, just how important is low latency going to be for those broader set of economic sectors and use cases, and what role will edge play in this? Well, the following is a snapshot of some of the latency requirements captured by the 3GPP in consultation with a number of key industry bodies and associations. And you can clearly see the wide range of latency requirements highlighted. For example, in mobile collaborative gaming, a target of 20 to 25 milliseconds end-to-end latency is required to guarantee a good experience with smooth gameplay and responsiveness. Another example here is transport and logistics for time-critical sensing and feedback. Here, a target of less than 30 milliseconds end-to-end latency is required. Now, of course, the question has to be asked, how important is it that these actual targets can be met? Well, if you take, for example, augmented and virtual reality, where motion to photon latency is critical for gaming experience, highlighted here in the green, this is the time between the movement of a tracked object and the corresponding movement being rendered and depicted on your headset. A high latency here can not only cause a loss of performance with the interactive graphics, it can also trigger something called cyber sickness, rendering the experience completely unusable. And another example there highlighted in the blue in the center is around automotive, where a latency delay could impact things like remote driving, reaction and interaction times, leading to accidents and even potential fatalities. And at the bottom there in manufacturing, time and precision critical applications, performance and accuracy could be degraded, costing millions of dollars in lost output and downtime to repair or recalibrate systems. And of course, latency must also be considered alongside jitter. You see, jitter is the variance or the inconsistency in latency across the network. And while having high latency is a bad enough problem, also having inconsistent latency or jitter can be even more damaging. Now, the example highlighted here on the left-hand side is with virtual reality, where high jitter can adversely impact the dual channels to the headset eyes. So if one channel is delayed from another, our right and our left eyes will not be synchronized, and then it's going to be headache and nausea central for the user. But not only do we need to understand user perception and acceptable tolerances that a human can cope with, we also have to realize that not all users are humans. Today's reality is we have connected machines, and it's obvious machines simply do not perceive. So while a human may be able to tolerate a reasonable degree of variance or inconsistency in latency, machines cannot. Mission critical machines in our factories need determinism. They need predictable latency that is tightly bounded by permissible maximums and minimums. A highly inconsistent network with fluctuating latency is not ideal for any type of industry adoption, nor for monetizing it as a guaranteed SLA. And of course, this becomes a network challenge. You see, latency is impacted by many facets, both inside and outside the network, as highlighted here on the chart. It's not just the air interface and the radio which needs to be tested, monitored, and optimized. Our core network processing and its distributed locations at the edge impact latency. Security implications or implementations add additional degrees of latency. Our underpinning transport domains made up of multiple technologies can create delays through suboptimal routing and bridging. While even external to the network, the internet and the applications add their own processing overheads. So one architectural solution being looked at by the industry to help reduce latency and variance is bringing the services and the applications to the edges of the network and hence closer to the user. The use of things like multi-access edge computing offers service providers the opportunity for localized processing closer to the user. And various options are now coming to the fore in the industry. So one option is to have the edge hosted at the peripheral edges or peering points of the telecom network, as you can see on the bottom left-hand side. This is usually in major cities, and this has the potential of reducing latency down to as low as maybe even 20 milliseconds. A second option on the bottom right, or the center there, is to bring the edge even further and deeper into the network, down to the RAN and the transport aggregation points or central offices, where latency could be potentially reduced to even less than 10 milliseconds. And a third option, which although isn't shown on the diagrams here, is to actually host the edge on the customer premises as part of a private network. This could potentially unlock latencies even lower due to the extreme localization of processing. And obviously, as part of this, you have the role of the public cloud, who are becoming more and more active in offering edge hosting solutions. This is potentially a high value capability alongside the enhancements being made by the 3GPP in terms of the 5G new radio and system. And you can see on the left-hand side here of the chart, the types or specific types of central to near and far edge solutions, which the public cloud providers are now starting to offer. And many telecom providers that we're working with today are already starting to explore and partner to offer combined solutions for both public and private edge offerings. And of course, the potential public cloud partnerships and the deployment options raise many questions which service providers and application developers are looking answers to. Is the public cloud really able to guarantee those lower levels of latency, to provide that levels of consistency and determinism required for SLAs and monetization? Are those locations, whether they're in large metro cities or they're down deep in the edges at zones, capable enough today? Because if the use of the edge and the public cloud can guarantee not only low latency, but also determinism, then enterprises may be willing to pay for the certainty of this assurance. And as part of that question, will enterprises pay? Sparent commissioned a leading analyst company, STL Partners, to conduct a demand-side survey. And the survey was with 150 enterprises in the North American market who are showing early interest in utilizing mobile edge as part of their 4G and 5G implementations. Now, the first key takeaway from the study is that enterprises see the primary benefit of implementing edge computing as improved reliability of service for latency sensitive services. And they also noted that the edge would allow them to enable new low latency use cases in the future. The second key takeaway here is that 56% of those interviewed stated they would be willing to pay for an SLA that guaranteed a latency window. Now, this is important. The term window, low latency alone is not enough. It must be consistent and bounded in a window that it never passes outside, as this is what the application will require for determinism. And the third key takeaway is that when we asked them about the latency numbers or ranges they needed, there was actually a genuine consensus around ranges that were not actually ultra low, but instead ranging between 20 and 50 milliseconds and 10 to 20 milliseconds. There was clear evidence of a sweet spot for low latency services where enterprises would be willing to pay for. But this opportunity may not be achievable or monetizable until consistently low latency can be proven and guaranteed. So how does the industry prove then and guarantee that edge can deliver not only low latency, but determinism that enterprises are going to require and that enterprises would be willing to pay for? Well, we believe this fundamentally comes down to new testing methodologies and proactive monitoring techniques, which my colleague Rich McNally is going to share with you, including real-world benchmarking and test results from commercial 5G edge and public cloud implementations. So I'll pass you over now to Rich as we explore the testing and the monitoring activities that have been going on.
Thanks, Steve. So yeah, as Steve mentioned, let's change gears a bit and we'll talk about different testing use cases and methods, results of some of the studies that we've done over the past year and the recommendations that we drew from those studies. Go ahead and pop to the next slide. So starting with different service lifecycle use cases that need to be addressed and what needs testing when. We break things out into three areas: design and launch assessment, continuous network monitoring, and customer experience management. So the applicable use cases for design and launch assessment are really things like edge zone launch, i.e. is my service ready to launch in a given city or market, to competitive benchmarking, i.e. How am I comparing to my competition? And then, always not to be overlooked, sort of the security assessment side of things. Under continuous network monitoring, we'll have the typical service assurance, network change management, service level validation use cases, but we see an even more critical need for latency segmentation and fault isolation, particularly due to the partnerships between operators and cloud providers, and the importance of quickly triaging where latency issues exist within hybrid networks. The last area, so realizing that potential of edge services is going to require attention to making your enterprise customers happy. To that end, it's really important to be able to model critical enterprise app traffic ahead of launch, but also ensuring that there's a way to address customer support and performance issues that come up along the way, and to base that on quantified, controlled results and not just anecdotal complaints. Go ahead, Steve. So let's talk through a couple of different ways to measure latency and jitter. So ping round trip time has been around for a long time, and it is, I think to this day, still the most common approach, but it really has its shortcomings. It's using ICMP, so it can miss the routing priorities that normal edge traffic would enjoy, given that it's primarily using UDP. It also doesn't delineate between up and downlink latency. Now, this is important because different edge applications can have different dependencies on either direction. And if you're not measuring it, you're guessing, really. Moving to the middle there, sort of UDP one-way measurements, it overcomes some of these shortcomings. Your test traffic is going to be routed properly because it's going to be using the production protocols. You can get separate down and uplink latency statistics. You can also vary the packet sizes and velocities so that you can emulate different use cases and traffic profiles. So these first two approaches are really useful for launch assessment, benchmarking, enterprise application emulation, and also useful for different service assurance use cases. But if we move to the right here, there's a new approach being worked on by the Broadband Forum and currently implemented by Spirent, that I think is quite interesting and should be really useful for latency service level validation, fault isolation, and different change management use cases. So Delta Q or QED, it's also UDP based, separates down in the uplink latency statistics. It goes another step further by allowing you to see latency contributions from geographic distance, from serialization/routing, and from network loading. So QED also uses this concept of a QTA, or a quantitative time agreement, to realize SLA commitments with customers. Go ahead, Steve. So in order to get a real sense of where we are currently and how things are evolving, we execute tests on publicly available edge services in different parts of the world on a regular basis. We did a recent study in North America and in Japan across 4 cities and 2 networks, in which we ran down and uplink latency tests at different rates. We ran the exact same tests to both the edge zones and to public cloud servers, appropriate for the city in which we were testing. The tests were all run on commercially available handsets, so nothing special there. We really wanted to replicate what real users experience. Moving to the next slide. So the good and likely expected news is that latency to the edge zones outperformed latency to the public cloud, and even got below 10 milliseconds in our Seattle testing. This outperformance, is seen in all cities tested and on both the down and the uplinks. Depending on the city, mean latency range from less than 10 milliseconds to the low 20s on the downlink, and less than 10 milliseconds to the high 20s on the uplink. So these results are for 5G traffic only, and really meant to show what can be achieved with wide 5G coverage and minimal handoffs between access networks. Next slide. All right, so as stated earlier, and Steve touched on this, sort of consistency is really critical for low latency MEC applications. It really means 2 things for the industry. One, consistently low latency within an individual task or session really ensures that the MEC service is fit for purpose for the selected application. And 2, consistency across relevant coverage areas within a city and in all the target cities that a given customer, whether they be enterprise, government, or consumer, where they're operating. So consistency within task and consistency geographically. Our study shows real differences between cities and how the down and uplink is characterized. Downlink shows more consistency in the cities tested in the USA and uplink in Tokyo. We also analyzed how consistency or variability is impacted as data rates increase. Downlink latency remained relatively consistent in New York and Chicago, but increased significantly as a percentage of means in Tokyo and Seattle. So lots of work to be done here, again, to ensure that geographical and in-task consistency. And when optimizing these types of services, it is really useful to compare variability of the edge latency to the cloud. Similar variability would indicate a stronger influence from other factors such as coverage or heavy interrupt. So it's also a useful exercise to compare the study results that we saw to the target latencies called out in the 3GPP specs. In this initial exercise, we compared the targets to average latencies observed in the 4 cities. On the one hand, we see a mixed picture where many use cases are supported by the currently observed results. On the other hand, you can see a good number of applications that require additional improvement, or cities that need additional work to realize the full potential of low latency edge services. Comparison of the targets to 1 sigma out or to a specific percentile, say 90th, would show that even more work is needed to broaden the use case coverage. So here's a quick architectural look at test infrastructure to support really successful edge launch and operation. I won't dig into too much detail here, but I think it's really based on some key tenets here. Really, you want to measure end to end and in between to know, not just what the customer experiences, but where and how to address problems that arise. Active testing, both end to end and within the network, are really critical to capture issues before users do. And the third thing is these capabilities really need to be sort of at the ready. Not everybody is going to be doing a lot of pre-testing before launching, and you need to be ready to operate in an environment where problems come in, or you uncover problems and need to turn solutions around quickly post-launch. So we're going to wrap up here with just some recommendations that, the studies that we've done, that we've drawn from them. As always, there's still much to learn, and it is early days with edge services. But as we begin to realize the potential of these services, we need to continue to sort of take a look, take a temperature of where we are, and continue the assessment we've been doing for the last year and a half. So as stated, it's really not just about means and medians. It's, consistency is critical. In some cases, I'd expect that, that focus on consistency to potentially outpace, the public's sort of historical overemphasis on throughput. Measuring to the end user or from an application perspective is really the only way to truly ensure that the end-to-end latency and jitter is acceptable for end user applications. As with the Internet of Things, there is no single MEC application, not a single latency requirement. When testing, it is important to model different data footprints of important applications. There's not one test case that covers everything out there. Handoff between different access networks can have a meaningful impact on latency, and we expect it will for a while. We have to consider that bringing new services to different cities and the geographies of target customers is going to have to take that, your plans will have to take that into account, because it won't happen overnight. A similar point can be made about challenging RF environments, especially for MEC applications that require high mobility. A big lesson that we've learned is, you want to avoid delays in testing that can result from not planning ahead to ensure that you don't trigger different service shutdowns due to network security procedures, both to cloud and edge zones. You have to be careful not to trigger denial of service sensors and things of that nature. Lastly, actively measuring key KPIs like latency and jitter it's always step one in ensuring service readiness. When problems are found, simultaneous logging of what's going on over the air, in network, and really active test-based service assurance with technologies like QED, those will give you the information that we need to optimize these services and ensure customer satisfaction.
All right, Stephen, Rich, that was a really insightful presentation and a really important topic. I wish we had time to get into it, but there really is a lot to that idea of continuous testing and the move to cloud native automated networks, and how does an operator really deliver on an SLA in a reliable, monetizable fashion. So I really appreciate you giving us a look at the work that Spirent's doing and sharing your perspective with our audience. So thank you again, guys, and everyone stay tuned for more here from the Mobile Edge Forum.